Today we have 10 to the 30 cells on the planet, which is a huge number that's really difficult to comprehend. It's probably more stars than there are in the universe, for example. And once we have that number in place, we can assume that the rate of primary production, which sort of fuels all the organic matter for all the other things that live on Earth, if we can get an estimate of that at different time points in Earth history, this gives us a way to estimate how many cells would have existed at that time. And if we do that again and again and again over different intervals of Earth's past, we can cobble together an estimate that, in our case, we suggest about 10 to the 39 cells have ever existed on the planet.
But again, how did you estimate that? Did you start with like microbial mats from, let's say 3.8 billion years ago? Like, how did you determine starting conditions, and how did you determine how much life there would have been at a given point?
Great question. So we always like to start in the modern environment where we have much better estimates of exactly what's happening. And by having the modern ratio of productivity to cell numbers, then we could take ancient productivity and relate that to cell numbers. But when we get back really, really far in Earth's past, we have to start making more and more assumptions. So, for example, when did life first evolve on the planet? That's a really contentious question. And the specific date is quite fuzzy. But we believe that it's somewhere between when the Earth finally cooled off enough to have an environment that was conducive to life, something around 4 billion years ago, and when we really see the first evidence of life, which is around 3.8 billion years ago. And so we sort of have it must have evolved somewhere sort of in those bounds. But because the biosphere would have been so much smaller in Earth's past with, for example, there likely wouldn't have been oxygenic photosynthesis, which fuels most of the planet today. And if the biosphere was a lot simpler and it would have been sequestered to sort of these niche environments, it would be so small that it sort of gets lost in the wash of these calculations. It's only until about 2.4 billion years ago where we have really good evidence that the atmosphere became oxygenated, and we would have had a much larger biosphere because of oxygenic photosynthesis just drastically increasing the amount of cells on the planet, that we have the majority of the action happening. And once we have constraints for these sort of critical intervals of time, a lot of the less well-known things sort of fall out in the uncertainty.
Okay, so what is the current estimate? Like, what is production defined as? What is it for today? Let's start with that.
Yeah, so production is the amount of, you can think of it as the amount of CO2 that's incorporated into organic matter. And today that's about 250 billion tons, which is it's about 250 billion tons, and it's produced and the consequence of that is like 10 to the 30 new cells produced every year.
Okay. So again, how many are existing at any one point? How many are dying? How many are being created? Is there a net upward trend of life, or is it stable?
So every single year, so if I was to take a snapshot today of how many cells are on the planet, it would be about 10 to the 30. But maybe unintuitively, most of that cell volume is actually in the subsurface or most of the cell numbers in the subsurface. But these are things that are growing incredibly slowly because there's just not that much energy there. But we can project quite deep into the Earth's below the Earth's surface. However, if we just look at cellular turnover times, we actually get a pretty similar number at about 10 to the 30 of new cell production each year. And so when we look at the geologic timescale going from the first life to today, there does seem to be an upward increase in the numbers of cells that have inhabited the planet. When we move into more recent times, of course, that value has probably fluctuated over the past, say 300, 400 million years once land plants colonized the continents. But for the most part, when you look over, say, 4 billion years, it appears that, yeah, we've increased the amount of life on the planet quite substantially.
So what fraction of life on the planet is metabolically active, and which doesn't even really, like you could say it probably almost doesn't participate because it's so slow?
Yeah, it sort of depends on the time frame that you're thinking about. So if I said at this exact moment, okay, likely not as much. Most of the active stuff happening is obviously close to the surface. In terms of the actual fraction, I don't have that exactly off the top of my head.